Hi, everybody, and welcome to this, our first episode in a new podcast series called Beyond. It's my absolute delight and pleasure to welcome my friend and colleague, Professor Emeritus David Brough, renowned author and speaker, and also worldwide astronomer. David, thank you for joining us today on our first episode of Beyond.
Oh, Andy, it's lovely to be looking up beyond with you. Yes.
So, David, the purpose of our first episode is to talk about the new James Webb telescope. Just tell us about the telescope. Why is it so significant? And what was the intention behind it when it was launched in December 2021?
Yes, that's really a very brilliant question. And I've devoted some 30 odd years, if not more, to infrared astronomy. Now, why infrared astronomy? Because our universe, we live in an incredibly dusty universe, a universe filled with cosmic clouds of dust and gas. And the point going back to 1990, in fact, I have a little image here of our first image, dust-penetrated image in Nature, which is the world's most prestigious astronomical journal. But that goes back to 1990. The power of infrared astronomy is this, Andy. You can actually probe clouds of cosmic dust. You can actually look through the clouds. It's like the X-ray. The X-ray can penetrate your spinal column, but I cannot see your spinal column. So I've had this great interest since 1990. Basically in infrared astronomy. The optical region of the spectrum cannot penetrate these dust clouds, but infrared can. But the issue's always been is, where are our infrared telescopes? Well, we get infrared detectors, for example, in Hawaii, in Chile, and elsewhere. But the dream was always to put up the world's largest infrared space telescope. That was the dream. Now, when I grew up, the largest telescope was at Mount Palomar, which you would know. That was a 5-meter telescope, optical largely. And the James Webb is astonishing. The mirrors, which we'll discuss in a minute, very complex, span 6.5 meters. So it's the world's largest infrared telescope, and it's in space. So you've got this incredible advantage that it's not subject to any light pollution, city pollution, and so on. It's in space. It's the world's largest space telescope, and its key function, the key plus above any other telescope, is it's the largest infrared, but it's also infrared. It's an infrared space telescope, and it enables us to look through the shrouds of the night.
So, David, the BBC put out a fascinating graphic on some of the key differences between the Hubble telescope and James Webb. Just talk us through some of those comparisons, if you would.
I'd love to, Andy. So the mirror size, a very complex mirror, which we'll discuss, looks like a honeycomb. The mirror size is a staggering 6.5 meters. That's unprecedented compared to the Hubble, which is 2.4 meters. Also, the operating temperature of the Hubble Space Telescope is at about 20 C, whereas the operating temperature here, very cold it has to be because it's infrared, is at about minus 230 C. The Hubble telescope is orbiting the Earth. The James Webb is behind the moon. So from that point of view, there's huge leaps in technology. Why? Because as you can see in the schematic, Hubble was launched in 1990. James Webb much more recently, in fact, last year on Christmas, around Christmas. The lifespan of Hubble is longer, but of course you've got it's like using two mobile phones. The one's really, say, BlackBerry and rather outdated, and here is your latest iPhone. So as you can see, in terms of, and also in terms of mass, Andy, 6,200 kilograms for James Webb, much heavier for Hubble at 12,000. So it's newer, it's lighter, but also something I want to really home in here, the mirror is not one piece. When I grew up in astronomy, telescopes had a mirror of a certain size. This one, if you look at that picture you brought up with the honeycomb, it's just staggering. It's made up of, I believe, something like 18 hexagonal segments, which are color-coded yellow in this image. And you can see that. I mean, it's incredible. And so when the telescope was launched into space, this whole thing folded up like a flower. Can you believe this? An entire telescope, the mirror actually folds up like a flower into your Ariane B rocket, and your Ariane rocket then takes it into space. And what happened now in the last couple of months is the mirror unfolds. It's like the opening of a flower, a petals. It's staggering. And the alignment is staggering. And when you look at these new images, one released by President Biden, it's just unbelievable how accurate the alignment of these 18 mirror segments really are.
David, I think I read that there was some damage over the period during May to the mirrors, and yet because there are multiple mirrors, we're still able to get these high-quality images.
That's the incredible, that's the strength. That is the strength of James Webb having the segmented mirrors, is that even if a tiny asteroid, and we were prepared for this, by the way, but even if a tiny asteroid or a little meteorite strikes one of the mirrors, you just adjust it, you use the other 17. It's no train smash, as you can see. In fact, we anticipate that the telescope will be bombarded by space debris over time, but it doesn't affect the images at all.
All right, so this is the image everybody's been so excited about, the image that President Biden released last week. Talk us, yes, David, what are we seeing? Why is this so significant?
Well, I look upon this really as the fingerprint of God, and I'll tell you why. We're looking back about 800,000 years after the Big Bang. We're looking back nearly 14 billion years in time. We're looking back to the time when the first galaxies were created. We live in an expanding Big Bang universe. And of course, we're always looking back in time. But the reason this is so exciting is for two specific primary reasons. The first one is you're looking back to the era when God created the cosmos. A mere 800,000 years post-Big Bang. That is staggering to think that we're looking back nearly 14,000 billion years in time. It is staggering. My estimate is that we're looking back between 600,000 to 800,000 years post-Big Bang, which means that we're looking back around 14,000 million years in time. It's staggering. You're looking at the first objects in the universe. But not only are you looking at the first objects in the universe, Andy, but you've got these arcs everywhere. You've got these pink arcs everywhere. They're called gravitational arcs as a result of gravitational lensing. You see them everywhere. What a glorious confirmation of the genius of Albert Einstein, right? Albert Einstein, in his mind, with general relativity, envisaged space and time to be curved in the presence of gravitational force fields. And here you can see these gravitational arcs all over the place. And you'd expect them. Why? Because we're looking back some 14 billion years in time. So the light from these distant proto-galaxies can pass through foreground galaxies, the gravitational force field, and create these stunning arcs. And yes, I mean, this image has been featured on every news medium, basically around the world, released by President Biden himself. But I also see it in a sense as the fingerprint of God. Why? Because it's the very first. It's the first. It's the first galaxies. It's containing the first stars. In astronomy, we always like to be able to look back in time further and further. And with Hubble, you can only do so much. This is going right back, but also right back in the infrared. And that's what, in the infrared, that's what makes this image so special.
David, it really is incredible to listen to you when you talk about years and hundreds of millions of years. It just puts it into a whole different perspective. Maybe for those of us who are not familiar with the maths, and you talk about a light year, what is a light year? How far is that?
So with a light year, it's basically the distance which light travels in 1 year. So let's just give you a nice analogy here. Light travels at 300,000 kilometers per second. And what this means is that light has been traveling at 300,000 kilometers per second, and it's taken 14,000 million years to reach our eyes at a velocity of 300,000 kilometers every second. That is the staggering math.
It's absolutely mind-blowing. The other image which was produced from James Webb, David, which you sent me yesterday, is these cosmic cliffs. Absolutely spectacular. What are we seeing here? Talk us through it. Talk us through the scale.
This is a really beautiful walk down memory lane because, as I say, I've been working on cosmic dust since around 1990. And I knew then already that we need infrared arrays, infrared camera arrays to probe stellar motility wards, Andy. And that's what you're looking at here. You're looking at, it's part of in the constellation of Carina, southern constellation of Carina, and you are looking at a swath of baby blue stars, which you can see, especially towards the upper right of the image. Baby blue stars have been born. The stellar radiation, the winds, we call them solar winds, if you like, stellar winds. The stellar winds are impinging upon these cliffs. They're impinging upon these cosmic cliffs. And so you've got writhing, seething, giant molecular clouds, this brown region towards the bottom, writhing, seething, and you've got an interplay, almost a collision of the worlds in collision, right? You've got baby stars being born and they're busy eroding out their natal cocoons. That's what's happening. They're eroding out their natal cocoons. And you can actually see very beautifully here the radiation impinging, almost like glowing steam, if you like. And you see that almost like glowing steam in the upper right-hand area of the frame. But again, this image, I think what excites me so much about this specific image is that it's stars in the making, but captured through the world's largest infrared space telescope, the James Webb. And it's a tiny, tiny, tiny swath of the sky. It really is. But the reason this is so interesting is simply the detail. I think it's like a gynecologist on Earth might put some instrumentation on the mommy's tummy and look how the little babies are doing. Here we're doing it in space. We're doing it within our Milky Way galaxy. We're imaging these, this writhing, seething radiations impinging on the cosmic dust clouds. And I think it's important, not only here in South Africa, but around the world, Andy, for people to be looking up. We live in a very dark world, not necessarily literally dark, as here without power, but I think in general, there's a gloom and a doom. Following COVID, people find it very difficult to look up. They really do. And I think that James Webb, and that's the reason we're doing the podcast together, and I'm so privileged to be working with you on this, is that we're looking beyond. That's hence the title, which Liz suggested. Beyond, we're looking up to the majesty and the awe, but also you, of course, are an expert with cutting edge technology. And this James Webb is cutting edge technology like one cannot believe in terms of folding mirrors behind the moon. It is absolutely staggering. And to think that you and I can receive these images on our computers is even more staggering.
David, we've got so much more to talk about, and that's going to be in future episodes. Let's leave it there for today. Thank you for joining us on this Mandela Day for our very first episode of Beyond. Thanks, David.
How special. Thank you, Andy.